Our next unit is going to be on projectile motion, and in this lesson we're going to basically look at three things, really one big thing. Projectile motion is really just one topic we're going through here, but basically what it is, it's motion in two dimensions. Previous cases we've talked about have been motion only in one dimension, but we'll look at two. And we're going to look at two different cases of projectile motion. With the initial condition to be horizontal, the velocity originally is moving horizontally. And the second case is that whenever the initial velocity is angled, it's pointing up. And so let's sort of get on to this right here. So in our previous units, all motion and equations of motion that we've looked at have all been in one dimension. We've talked about, a velocity traveling in some direction here. But really, when we've dealt with the acceleration on it, the acceleration has been in the same direction as the velocity. We haven't had any cases where, say, we have a velocity which is going this way, but the acceleration is instead pointing this direction. We haven't dealt with anything like that. Our accelerations have always either ended up being going the same direction as the velocity, or they've been going the opposite direction as the velocity. And so that basically left things in one dimension. It left us a nice set of equations, made it a little easier to solve. In this case, though, we are going to look at a situation where we basically have an acceleration which is going in a different direction than the initial velocities. Now, it may have a component, as we'll talk about in a little bit, in the same direction as the acceleration, but there is a part of the velocity which is not going in the same direction as the acceleration. And this is called projectile motion because this is what happens whenever you throw something in a gravity field. Is that, if you basically here's a person sort of standing right here, gravity is pointing down, that's the direction of the acceleration, but when you throw it, you're generally going to throw it at some angle. And so in this case, the original velocity of that object is not in the same direction as the acceleration, and so as a result, this thing will take a nice little parabolic path as it sort of goes through the air, because it is being accelerated in one direction, but has a component of the velocity in another direction. Now, you notice we've used this term component several times here, because that's the critical piece that we have whenever we're basically setting up a projectile motion problem. So we say, second point here, in the same manner as we can express a two-dimensional vector, so, something where we have a vector going this way right here, we can break it into components. We have an x component, we have a y component. And so we can sort of do that little trick right there to find whatever value of our vector that we have here. And then once we've got that, we can manipulate the individual components. You remember, we broke things in components, and once we did that, we could add up, if we're adding vectors, we could add up all the x's and then add up all the y components and use that to manipulate them. We can also express, in the same way that we did with vectors, we can also express two-dimensional motion, that is projectile motion, in terms of x and y components. And what do we mean by that? Well, let's take a look. So let's have an example of a shell is fired at 40 meters per second at 45 degrees above the horizontal. And so what we have here is we have sort of a level plane that goes across here. And for this level plane is that we have a shell which is fired at an angle of 45 degrees and with a speed of 40 meters per second. So right up here, that's sort of what we set up here. Now when we fire the shell like this, it's basically going to take, if I can draw this out here, it's going to take a parabolic path. It will travel through the air because of the fact that there's an acceleration on this thing which is going down. If it's on Earth, it would be negative 9.8 meters per second squared. I don't think I can fit that in, but that's the unit on there. This is basically what it's going to do. Now, when we talk about expressing the motion in terms of its x and y components, here's basically sort of the trick to this. Let me erase a little bit of the end so I have a little more space here. All right. We are going to look basically at x, and we are going to look at y. And we are going to look at all the different components of motion we talked about in our previous equations in terms of x and in terms of y. So previously we talked about acceleration, so we're going to look at acceleration in terms of x, an x acceleration. We're going to look at acceleration in terms of y, a y acceleration. We're then going to look at basically an original velocity, VOx, and then an original velocity for y, VOy. We're going to look at the same type of thing for a final velocity. Not just a final velocity, but a final velocity in x and a final velocity in y. Just like that. We'll see if I can manage to fit all this in here. Next thing we'd have here, we've talked about acceleration, original velocity, final velocity. We'd have a distance in x and a distance in y. And then our very final one here is going to be a time. Now the time are sort of special because the time for x and the time for y have to basically be the same thing, and so these values are the same. There is no sort of x component of time and y component of time. It just doesn't work that way. But let's see sort of how we'd set this up. If we had a situation like this, we know that the shell is fired at 40 meters per second, 45 degrees above the horizontal. So let's see which things we know based on that. Well, the acceleration in the x direction, let's look at that one first. Well, the acceleration in the x direction would be how much it's accelerating going this way. And well, there's nothing pushing it that way. Gravity's accelerating it downward, but once the shell has been fired, because it's whenever we're dealing with these projectile motion cases, if they say a shell's been fired, we're talking about after it's been fired. We're not worried about what's happening in the barrel. So it's in the air, it's traveling, there's nothing pushing it in terms of x, assuming we're ignoring air resistance, which we will for this class. And so that means our x acceleration is simply 0. Our y acceleration, though, well, that's going to be the negative 9.8, our good friend that we've been using for quite some time here. The original velocity in the x direction, that's our next one. Well, we know the total velocity, that's 40 meters per second. But to find the original velocity in the x direction, we would have to take this existing one and break it into components to basically have a v naught x and a v naught y like this. And if you think about it, we already know that the angle is 45, the total is 40 here, and so let's say we're looking at v naught y. In this case right here, we have, with respect to the angle, we have an opposite side and we have a hypotenuse, and we have opposite and hypotenuse, then you're basically going to be talking here about sine. And so v naught y, in this case, would be basically equal to, if you rearrange it here nicely, v, the total speed, times the sine of your angle, v sine theta. In this case right here, that's going to be 40 times the sine of 45 degrees. Okay? If we go ahead and work that out, that let's see, v sine theta in that case is, let's see, if I'm doing my math correctly here, should be 28.28. And so that would mean that for our v naught y here is 28.28, I believe I said it was. 28.28 meters per second. So we've got that way. We're looking for v naught x would be sort of our next one over here, is that v naught x is going to be similarly, is that since it's an adjacent to the angle here, we have adjacent hypotenuse, that's going to be cosine, and so it would be v naught x is going to be equal to v, which is 40 times cosine of the angle, 45. Do that, and of course, since this is a 45 degree angle, it's going to be the same value here, and so still should be 28.28, and so that would be our original x velocity. 28.28, just like that. So when setting up our components, if you have something that's fired at an angle like this, then basically you have to find what the x and y components are of the original velocity. Once you've got those, you're good to go. You're good to go. So let's look at the next ones. Final velocity in x. Well, in this case, x is not accelerating. There's an acceleration of 0, and so since the acceleration is 0 here, that means the final velocity in x is also just 28.28. For VFY, no such luck. We don't know how to figure that out. We don't have that from here. That final velocity, in most cases, we really wouldn't know. In actuality, if you actually think about it, though, we actually could figure it out for this case because usually you won't figure it out, but in this case, there's sort of a special case because since it ends way over here at the same height it began, if you look at this parabola, it's symmetrical. And remember we said that the velocity is basically the sort of a distance graph is basically the slope. And so if you think about what the slopes of these two things would look like, then you sort of recognize that the slope of going at the beginning and the slope at the end, the x components aren't going to change, but the y components will basically flip. If I throw something up in the air at 5 meters per second, when it comes back to my hand again, it's going to be going negative 5 meters per second if I catch it at the same level that I threw it. Now, obviously, if I catch it at a lower level, it's going to be going faster. If I catch it at a higher level, it'll be going slower. But really, we could actually say in this case that our final velocity y, which only works in this case whenever you basically launch something and it ends up at the same height as where it started, is actually going to be just negative 28.28. In this case right here, turns out a special case where we can solve that here. Dx and dy, do we know what those are? Let's take a look here. So dx, let's say that we're going to talk about this sort of final spot here. Dx would be whatever this distance going all the way over here is. Do we know what that is? Well, not really. So we're going to have to leave that blank right now. We could probably figure it out if we need to. That's what we'll do a little later on. dy though, well, we're at the spot right here. Since we're at that spot right there, we know that the height is 0. So in this case, it started off at a 0 height, and it's going to end at a 0 height, and so the distance it travels in the y direction is 0 in this case. If we had ended up somewhere like, say, up here, then the dy would have been whatever this height is right here. That would have been what your dy was. In this case, we don't have to worry about that too much. The time would be basically however long it took to get to that point, and to solve those, we would basically have to use our normal motion equations the same way we have been. But this is basically how you go ahead setting up a projectile motion problem. You're going to set up basically a section in x, you're going to set up a section in y, and you're going to write out what each of your little variables are for all the different motion equations you have for all those things and plug in what you know. Will there be some you won't know to start with? Absolutely. But that's sort of where we start with, and then we can solve for them later. So let's go on here and try out an actual example and sort of see what this would look like here. All right, so once we have established the known conditions, that's what we did last time, is basically figured out what the initial conditions were, what we know, we can then apply our regular equations of motion to each component using these to solve the system. So the normal components, once we got our components, we're going to apply our normal motion equations, our distance equations, our velocity equations, our acceleration equations to be able to find those here. So in effect, what we have here is two independent sets of motion equations. We have x's and we have y's. And for the most part, these two are completely left separate. Is that we can do our distance equation, we can do our acceleration equation for this one. So we have a distance x and acceleration x. We can do our distance y, our acceleration equation y for this right here. And for the most part, these two are completely independent. They are independent of each other. The only things that relate them are two things. The time, which is the same for both of these, because the time is not of x, it is not of y, it is for everything. You can't throw something through the air and go from one point in time to another point in time and have it have a different time for x and a different time for y. They have to be the same. So those t's are going to be equal. That sort of crosses this barrier back and forth. And the other one is common trigonometric relations. And so, if I have something along these lines where I have a v naught x and a v naught y like this, and I have some angle theta, these are related. I can relate them by that angle here. The tangent of theta would be v naught y over v naught x in this case. And so I can also relate them through trig, basically. If I know an angle between certain things, I can use that to solve them. But other than that, x's and y sets of equations basically remain independent. They're sort of separate from each other. And by sort of using those two separate sets, I can sort of solve for the motion I'm looking for here. So let's continue. So I have a ball. It's rolled off of a 0.75 meter high desk at 1.1 meters per second. How far away from the base of the desk does the ball land? And so in this case right here, let's set up the conditions here. I have some sort of ledge. Here's my ledge right here. I know that it is 0.75 meters. That's the height that goes right here. I have a ball. It rolls off of this. It starts off going at a speed of 1.1 meters per second. And it's going, since it's on a flat surface, it's moving only in the x direction. Once it goes off, it's going to have this nice little track until it goes down here. And so that's sort of how we're going to set up here. So let's go ahead and write out what we know for our x and for our y. And so let's say we have x over here, we have y over here. And so let's look at what we know here. So let's look at A, the acceleration of x. Well, that's going to be 0 because, once again, there's nothing that's accelerating it in that x direction. It's just going 1.1. It'll continue to go 1.1 sort of indefinitely until some other force acts on it. For y, though, our acceleration in y, we can assume this is on Earth, and so it's negative 9.8 is going to be our acceleration, meters per second squared. Since we have units of meters and meters per second here, that's what we're going to want to use. So our next one would be our VOX. And so in this case right here, what's the original velocity in the x direction? Well, it tells us it's going 1.1 meters per second. Since that is rolling in a horizontal way, that's going to be our x coordinate right there. So we know that's 1.1 meters per second. V naught y. Let's see what we know for that one. What's the original speed of the object traveling in the y direction? So the instant this ball leaves the table, how fast is it going up or down? Well, whenever, this is basically the same condition as when you drop something, is that it's rolling on a flat table. It's not moving up or down. It's a flat table. And so the instant it leaves, it hasn't gotten a chance to accelerate yet. So its original velocity is simply going to be 0 again. And so this is sort of what we have here. So v naught x is 1.1, v naught y is 0. Vfx, do we know what this is? That would be the final speed. In this case, the question says, how far away from the base of the desk does the ball land? And so our final condition is going to be this spot right here. That's what we're sort of interested in. And so our final velocity in x would be whatever speed it has in the x direction at that point. Well, in this case right here, this object is not accelerating in x, and so that means the velocity is not changing, and so it's still going to be 1.1 for that. V naught y or Vfy on the other hand, we really don't know what it is. We know it starts off at 0. We know it's accelerating for some period of time. We could find the final velocity if we knew how long it fell for, but we don't know the time just yet, so we really don't know what Vfy is in this case. Our next spot here is going to be dx. And so dx is the distance it travels in the x direction. And so in this particular case, that would be the horizontal distance it has from where it started to where it ends. That is going to be our dx. We don't know what that is. That's actually what we're looking for. How far away from the base of the desk does the ball land? And so that is dx. That's what we're looking for. We don't know what it is just yet. That's what we want to find. Our next guy here would be dy. For dy, that would be the distance that it travels in the y direction. Well, it starts off on the top of the desk. It ends up on the ground. So that 0.75 we have right there, that is dy. The only thing is since it's falling, it's actually going to be negative for the purposes we have here. So it'll be negative 0.75 meters is going to be basically what we have for dy, because it starts off at some original height. It ends up 0.75 meters below that. So it's declined in its height by 0.75. So it's negative 0.75 meters here. Our last one here is going to be time. So we have time right here. We're not told anything about the time, so we're going to have to solve for it. So your next step is basically look at what you've got and see what you can solve. In this case right here is that we're looking for the basically see how far away from the base of the desk does the ball land. That's dx. So we want to find what this is right here. So we need an equation that basically relates dx and other things. Well, this in the x direction, it's moving at a constant velocity. Since we can basically separate x and y, they're independent sets of equations, there's no acceleration in x. There is an acceleration in y. There's no acceleration in x, and so we don't have to worry about the y acceleration. We just say no acceleration in x, and so that means it's moving at a constant velocity in x, even though it's not in y. In x, it's a constant velocity. And so our normal equation of constant velocity, velocity is equal to distance over time, would apply here. But to know this, we'd have to know the velocity, which we do, it's 1.1. We'd have to know the time, which we don't. So we're going to have to find that time before we can apply this little equation down here for x. So our key is now to find what the time is in y. Because if we can find the time in y, we'll know the time in x, and then we can solve our equation here. And so let's look at how we'd figure out the time for y. Well, for y, we do know the distance it travels, we do know the acceleration, and we do know the original velocity. That means we're probably, since we have this distance right here, it means we're probably going to go ahead and set up a distance equation. And so we say negative 0.75 is our distance is equal to 1/2 acceleration times time. Acceleration here is negative 9.8. 1/2 times that is negative 4.9 times the time squared plus the original velocity in this case, which is going to be 0 times the time. Fortunately, this term is just going to kick off. The 0 time goes away here. And so we have negative 0.75 is equal to negative 4.9 t squared. We'll divide both sides by negative 4.9 and then solve for t. And just to save some space here, I assume you can basically do the algebra going on here. If we go ahead and solve for t that way, I get it's 0.39123 seconds. Obviously, since this is a squared term, you actually should have gotten a positive and a negative value for this. Obviously, the positive value is the physical one. Oftentimes, whenever you're solving these, you will get a positive and negative, and remember that the physical value is the one you want to use. So we get 0.39123 seconds. That's our time. So excellent. Now we've got that, 0.39123 seconds. And once we've got that, that's also the same thing that's going to be over here. So now we can go ahead and set up our velocity equation. We know that velocity for x is going to be distance x over time. And so the velocity x, we said, is 1.1 meters per second. That's the value we're given, equals the distance x, what we're looking for, over the time, which is 0.39123 seconds. And so from that, we multiply 0.39123 times 1.1, and that gives us an x distance, in this case, of 0.4303 meters, which rounded to significant figures, looks like we have 2 sig figs in each of these here, so it'll be 0.43. So 0.43 meters is going to be our final answer. And so this ball will land 0.43 meters from the base, 43 centimeters from the base of the desk. And that's basically how you would work out a simple projectile motion problem in the horizontal direction. So let's look at another case of horizontal original motion. Let's see what we get here. So we say that a ball is rolled off a 0.75 meter high desk at 1.1 meters per second. What is the velocity of the ball when it strikes the ground? So in this case, I've given you the same initial conditions, 0.75 meters high, 1.1 meters per second. So let's go ahead and set up once again our table on this. So I have x, I have y. It would be nice to have saved those, but you'll get the idea. Ax is still 0. This object is still not being accelerated in the x direction. Ay is still going to be negative 9.8. This desk is still on Earth. For our v naught x, we're told it's 1.1. It starts off going 1.1 meters per second. And I guess we can go ahead and put vfx too, because we know it's also 1.1 right there. V naught y, initial condition, still the same, is that it's rolling off a level surface, and so it has no y velocity to start with. It's not being launched at an angle. We'll do those later. So vf, I did it again, vfy. We don't know. That's sort of what we're looking for here. We didn't find it last time, but we're gonna need this to find the velocity of the ball when it strikes the ground. Our next one would be the distance x, the distance y in these cases right here. The distance y, we know it's going to be dropping. It's going to be negative 0.75 meters. We already figured that before. And in this case, it says when it strikes the ground. That's actually the same point as what we found last time. And so we actually figured out in the previous problem that that distance is going to be 0.43 meters, which we know from the previous case. And so I'm going to go ahead and sort of underline that to show that this is not something you would know from the problem directly. This is something we had to calculate earlier. So we've got that. Our next one here would be the time, which fortunately we also figured out the last case. So this would be another one you'd have to figure out. Now, how would we figure out that time? Well, the same way we did last time, by going ahead and setting up our y equation, because we do know what the acceleration is. We know the original velocity. We know the time, or sorry, we know the distance. And you can use that to find the time, which we got, as we said, to be 0.39123. Like that. So 0.39123. Just like that. So basically, we know these values here. And I've got them in green in this case because of the fact that we calculated those earlier. Question is, what is the velocity of the ball when it strikes the ground? Well, let's sort of take a think at what this is going to look like here. And so at the very end, here's our ground level here. The ball is going to come down at some angle right into here, and it's going to hit the ground with some velocity. Now, since this is a velocity, this does have direction to it. And so it's going to have a y component, it's going to have an x component. And so we have this x component is basically going to be vfx, this y component is going to be vfy. That's going to be our two components here. We will need to know the angle. Now, typically, is there two ways of showing angle whenever you're basically dealing with projectile motion? If you have a case where you're launching something, is oftentimes that when you're doing that, the angle is basically the launch angle. That's this angle right in here. That's an acceptable one to do. You basically would say it's launched at this angle. Typically, that's what you'd mean by that is the angle between the launching and the horizontal. If you have something that is striking a surface, then basically that angle is basically called the impact angle. And so if something's coming in this way, if you measure this angle, that's called the impact angle right there. And so sometimes you can describe it with respect to the impact angle. If you don't use either one of those, you simply want to use your heading system the same way we did back in the vector unit. That is just as easy and just as accurate way of doing things right there. So This is sort of where we are right here. Let's say the velocity of the ball when it strikes the ground. We might as well go ahead and solve it, in this case, with the impact angle. And so we're going to look for this angle for our vector, because velocity is a vector here. And so we're going to try to get Vfy and Vfx and that little angle that's inside there. And so to do this, well, we already know one of them. We already know to start off with that Vfx is 1.1. because Vfx doesn't change. There's no acceleration in the x direction. Vfy, though, we're going to have to solve. And so for Vfy, we know the original acceleration, we know the original velocity, we know the acceleration, we know the original velocity, we know the time. We're looking for Vfy, and so those three equations are mostly all going to be, or those three values will all be used in our acceleration equation. Acceleration is Vf minus Vo over t. And so our acceleration, negative 9.8, is equal to Vf, which is Vfy in this case, minus the original Vf minus Vo, which in this case is 0, divided by the time, which we already figured out, 0.39123 seconds, like that. And it's 9.8 meters per second squared. So when we solve for Vfy, that's pretty straightforward to do. So we get Vfy. We do that. Let's see, if you just run the math there, you get negative 3.834. So negative 3.834 meters per second. It is negative. That confirms the fact that if you look at this vector right here, you can see it goes down. That's consistent with that. That's where that negative sign comes into. So first thing, let's figure out what the velocity is. Well, we know Vfy, we know Vfx. This is a right triangle, Pythagorean theorem. V squared equals Vfy squared plus Vfx squared. So V squared is going to equal 3.834 squared plus 1.1 squared. And if you do that, that should give us a final velocity V, which is, of course, our hypotenuse here. Let's see, doing the math on that, 3.988 meters per second, just by plugging into Pythagorean theorem. Just once again, just save space on here. And so we've got that right there. Next thing to do is we'd want to find what this impact angle is. Well, for this impact angle, we know the opposite, that's Vfy. We have the adjacent, that's Vfx. If you have opposite and adjacent, that's tangent. So tangent of theta is going to be equal to opposite Vfy, 3.834 over Vfx, which is 1.1. Note that we didn't use the negative here, is that once we got our triangle set up and we noted and we confirmed that the direction on that vector was going down, we don't have to worry about that. We're just interested in the magnitude of each side at this point. And so we'll take arctangent of 3.834 over 1.1, and that gives us a value for theta of, let's see, arctangent of that, 74.4 degrees. And so if we looked at our final answer here, since we had two significant figures involved here, would basically be 4.0 meters per second with an impact angle, so at 74.4 degrees. And really, to show it's an impact angle, we'd basically say above horizontal. If you're not going to use a heading, you need to specify. If you choose to use a heading, you can just say at that angle and you're fine here. So, but if you are talking to impact angle, if the question asks what's the impact angle, the answer is just 74.4 degrees, straight up. If it says what is the velocity, you need to specify what the angle is from if it is not a heading. Headings, you can just say at that angle and it's implied to be heading. That's going to be the convention for this class. But this is basically what we have here. So let's sort of move on to our next example of what might happen here. So, if my computer will let me do it, there we are. So, a ball is rolled off a 0.75 meter high desk at 1.1 meter per second. What is the speed of the ball when it's halfway to the ground? This one's a little different than one we did last time. The initial conditions are still the same. We still have our nice little desk here. We still have that it's 0.75 meters from here to here. The ball is still going at 1.1 meters per second this way. But the difference is that we're not going to follow the whole 0.75. This ball is going to go, as it goes here, we're interested in what happens when the ball is halfway to the ground. It's this point right here that we're interested in, not the bottom point. And so in this case right here is that our distance in y is not 0.75, it's half of 0.75. So in this case right here, that would be just 0.375, because that's 0.75 over 2. And so let's set up our table again. So for our table, we have x, we have y. Most of these are going to be the same as what they were before. The acceleration in x is still 0. The acceleration in y is still negative 9.8. That hasn't changed here. The original velocity in x is still 1.1, because that's still an initial condition. That's the same here. The original velocity in y, because it's not moving at an angle to start with, is still 0. The final velocities in x and y are not going to be different, though. This is not going to be the same as what it was before, because previously it went all the way to the ground. In this case right here, it's not going all the way to the ground. And so we can't necessarily say that these are going to be the same values what they were before. Now for x, since it's 0 acceleration and it starts off at 1.1, that one will be the same here. But it's not going to have the same VFY as it did in the previous problem, because it's obviously going to be going faster when it reaches the ground than it was when it was only halfway to the ground. So that's what we've got there. So next one would be our dx and our dy. This one also is different from previously here. The dy is now not negative 0.75, it's negative 0.375, half of 0.75, because it goes halfway to the ground. Dx we don't know anymore. So we're not certain on that one either. And then we have time for these two guys, which we also don't know. We knew the previous one, we don't know this one. Now, note that just because it goes halfway to the ground does not necessarily mean it has half the time, because the object's accelerating. And so it's going to cover that last half of the distance in less time than it covers the first half of the distance. So that's sort of a pitfall to watch out for. You cannot assume that just because it falls half the distance means it's going to take half the time. And in fact, that would be incorrect if you did assume that. So let's take a look at sort of what we've got here. So the first step is basically going to be to try to find the time, because that's the only one that goes really between both of them. And so looking at things, we really can't solve things on x because it's moving at a constant velocity, and so we need the distance and the time and the velocity for that. We only have velocity. For y, we do know the acceleration, original velocity, and distance. And so that's the one we're going to set up first, looking at the distance equation for y. And so setting that up, we would basically say the distance it travels is negative 0.375, so 0.375 negative is equal to 1/2 acceleration, which 1/2 times 9.8 is 4.9, times t squared, plus v naught t. V naught is 0 times t. That term once again cancels. Very nice. And so we end up with negative 0.375 is equal to negative 4.9 t squared. So divide both sides by negative 4.9, solve, take the square root of that, and we're going to get that t equals, in this case, 0.2766. 2766 seconds. So we know those now, 0.2766, 0.2766. We've got those right here. We are looking for the speed of the ball when it's halfway to the ground, and so we'll need to know both VFX, which we know, and VFY, which we don't. So we're going to solve for that VFY. And so to find that, if we're looking for the final velocity, we're going to use our acceleration equation. So negative 9.8 is equal to final velocity, VFY, minus the original velocity 0 over the time, which we just found, 0.2766 seconds. And so in doing that, so we look for VFY right here, would be 0.2766 times negative 9.8, and then add 0 to that, which obviously doesn't change a whole lot. And so when you do that, I get 2.711 meters per second. So 2.711 meters per second. And so that lets us sort of set up our final triangle here. We know at this point, it is moving in this direction right here. So it is going to have both y and negative y, which actually technically this was negative, wasn't it? Negative y and a negative and a positive x coordinate here. We know that the x is going to be the 1.1. We already said that was our final velocity in the x direction. Our y is going to be 2.711 is going to be our y velocity here. If we're looking for the speed, speed is, remember, not a vector. That's just a scalar. That's just what our velocity, our magnitude of the hypotenuse is right here. And so Pythagorean theorem time. v squared is equal to 1.1 squared plus 2.711 squared. And so when we solve for that, I end up getting a velocity in this case of 2.93, which would round to 2 second figures, so 2.9 meters per second. So 2.9 meters per second would be our final speed of this ball when it's halfway to the ground. So this is basically how you do a case of projectile motion where it has an initial direction, the horizontal. And so we're going to go ahead and end this video for right now. Is that the next video on here, part B, will basically deal with projectile motion when the initial conditions are not horizontal, they are vertical.